Okay, so number 2 in the homework. Oh no. Sure hope I saved everything. All right, I think I did. All right. So here was this was number 2 from the first part on the arc length. So here is x equals g of y, where g of y is ln of y, and shown from y equals 1 to 4, right? Lowest y value 1, highest y value 4. Okay, so I have a series of tasks here. The first task I want you to do is define the arc length function for g in terms of y. Can you do that? Can you define the arc length function for g in terms of y? Go. See if we got the basics down here. You're up. Can you tell me? Did you get the arc length function? Okay, hold on a sec. Hold on a sec. Start again.
It's a little less than a to y, so we have the integral from a to y.
Integral from a to y.
Of the square root of 1 plus 1 over y squared dy.
He wants the integral from a to y of square root 1 plus
1 over y squared.
Okay, so what would this be? This would be the derivative of our function with respect to y. So you could use I could use the total derivative in GC and then do derivative of g. I'm going to actually do that, but I think, he said 1 over y, which is perfectly fine. But I just want to point something out when you do this, that when you come in here to do this, so now I'm going to do g of y. Is it correct?
No.
Because? I got to get dy in the bottom, right? So with respect to y, so I got to change that to y. All right, and then squared. And then dt at the end.
We have to change the y.
Okay? So it's just changing that t enough.
No, we have to change the other y.
All right, so yeah. So we're thinking about this thing as dg dy. dg of y dy, but because it's our rate function inside an integral, we also need to change all these to t's. Did you catch it? How'd he do? What do you think? It's good. He also said this could also be what? Inside here? 1 over t, right? So 1 over y would be the derivative of g. But then because it's in our integral, we need 1 over t. So 1 over t would be fine too. And that's what he said. Okay, next task. We want to graph the arc length function in the right-hand pane. Okay? Now here's the thing. I want to put the independent, what's the independent variable of our arc length? Y. I want to put the independent variable on the horizontal axis. So y values over here, I want to put on the horizontal axis. And then on the vertical axis, I want to put arc length. So as I'm looking across this axis here, what will these values mean? Y or g of y? Y values, right? They're going to be the independent variable. I want that. So here's my independent variable here going up this axis here. As y changes, we accumulate arc length. So now over here, I want to have this to be y, and then I want to track how much arc length I've accumulated on the vertical axis. So what will I write in GC to do that? What will I write in GC to do that? To accumulate arc length on the vertical axis as a function of the y values over here on this horizontal axis. Any volunteers? How will I do this in GC? So first of all, how do we graph something in GC? Just in general, we've got a function. How do I graph that function? Yeah, so like y equals f of x, right? So y equals f of x. So now that's the idea of graphing the function f, putting the independent, this is going to put the independent variable on the x-axis, and it's going to put the dependent variable on the y-axis. So what am I going to do to get, what am I going to do here? So what do I want, in this graph, what do I want the y to equal? What did I want on my horizontal, vertical axis? Arc length. So I'm going to make y equal to what? S. So y is going to equal S of G. Now the key is what's going to go inside here. So this is saying take values of the dependent variable of the arc length function and put them on the y-axis. That's what that's saying. Okay, that's what we want. All right. So then what will our first argument be here? But I want to graph this now, right? So remember what this looked like? I lost my graph button. How did I do that? How did I do that? There we go. Okay. So if I graph this, all right. So what do I want to graph this now? So my argument for A is going to be, yeah, the first value of the independent variable is going to be 1. All right. And then what's going to be my independent variable? So what did I want to do? I want to take the independent variable and I want to put it on the horizontal axis over here. So what should this be? X. Okay, so what is this doing? So this is the independent variable of my function s, but I want to put it on the horizontal axis. So I want it to be x. Does that make sense? And I want to start at x equals 1. And then I want to take values of the arc length and put those on the vertical axis y. All right, so then I want to put that over here on the right-hand pane. And to do that, in GC, what you do to get graphs in a second right-hand pane is you use apostrophes. So I'm going to do apostrophe on the y, apostrophe on the x. Now that is not prime for derivative. This is GC's way of saying open up a second graph window on the right using apostrophe. So that's not y prime and x prime. It's y apostrophe and x apostrophe. And that's going to open up the second pane and graph it over here. All right, what will that look like? So what will that graph look like? When I turn this on, so I think I have that in the next line here. So when I turn this on, what are we going to see? Can you make a sketch of what that'll be? I'll take a few more names. So think about that, talk about it. What will this arc length function look like? I've put the independent variable y here and the arc length on the y-axis by writing that command. I'm going to turn it on. We're going to get a graph. See if you can figure out what that graph's going to look like. X. So x at 1. So at 1 right here, what will the value of the arc length be? 0. So it'll start at this point right here and then do what? Go up. Up. As x increases, or as, in this case, as y increases up this y-axis, we get more and more arc length. So now our y values are on the x-axis over here. So as y increases, our independent variable increases, we're going to get more and more arc length. Okay, is this what you thought? Again, imagine so when we look at this axis, we're thinking what's along this axis? The y value on this graph, right? And as y increases, what happens to arc length? Increases, it accumulates. So how would we represent the total arc length of the red piece there? So how would I represent the total arc length of the red piece? Dylan. SG of, he said 1 comma 4. Is that the whole length of the red piece? SG of 1 comma 4. Yep, that's it. Because we want, starting at 1, we want y to be 4, and that will be all the accumulation of arc length from there to there. Have that. So let's put that in. S sub g of 1 comma 4. And how does that relate to this graph over here? So how does that, what I just typed in, S of g of 1 comma 4, and then it gave me 3.34, how does that relate to this graph over here?
Should be the y output. The y point.
What is it?
The y point on whatever corresponding x comma y.
So you're saying you're looking at this as for x equals 4?
Yeah.
So when x equals 4 on this graph, then, can you read that? So I haven't quite gotten to 4 yet, but is that almost what we got for the arc length?
Yeah.
Yeah, okay. All right, so now I want you to, here's a point, 2 comma 1.22. 2 comma 1.22. I want you to interpret that point. What is the meaning of that point? Go tell the person next to you. What's the meaning of that point right there? What are these down here? These are the y values on this graph, right? Because when we defined the function, our independent variable was y, and then we said take those y's and put them on the x-axis when we graphed it. So these are still y values on this graph. So when the y value on this graph is 2, the 1.22 is what? So what is 1.22? Arc length from
y equals 1 to y equals 2.
Right. It's the accumulated arc length starting from 1 up to when y equals 2. So it's that much arc length. That's the 1.22 that we're getting from this y coordinate over here. It's that much arc length. Is that what you said or thought? That's what you should have thought. Okay? Or said. All right, very good. So next question. Now we're going to do surface area. Okay, I'm going to rotate that curve around the x-axis. Okay, I'm going to rotate. Any questions? Anybody have a question? Yes, please.
Is there a way to tell DC to zoom in on a particular point on the graph?
Yep. So yeah, like this one right here. So when you do have you done the crosshairs before? If you just click on the graph, it gets crosshairs, and now once the crosshairs are up, if you just zoom in, it'll focus on that point where the crosshairs are. Is that what you wanted?
Tell it like I want the point x equals 2.57 or something.
You'd have to slide this until it gets to the one you want. And if you zoom in far enough, you should be able to. So if I want 2.5 exactly, there's 2.5 exactly, because it's going to do it on nice. It'll do it on nice points. Does that help?
Yeah, I was wondering if there's like a specific way you would type in hey, x equals 2.7245 or something like that.
Not that I know of. I think you have to just do it manually.
That's fine.
Yeah. Okay. So now we're going to rotate this curve around the x-axis. Okay, around the x-axis. Which is the x-axis? The horizontal or the vertical? Horizontal. The x-axis is this one. So we're gonna, if we rotate that around the x-axis, what will we get? Kind of like we'll get kind of like the bell of a horn, right? Like the bell of a horn that's been chopped off. So it's you could put your hand right through it, right? You could put your arm right through it. And we want the surface area. We want the surface area of that thing. Or better yet, we want a function for surface area for that. Okay, so we're rotating around the x-axis. So our frustums, or ribbons, right? We know with surface area, we model those with these things called frustums, which are like pieces of a cone, like chopped off pieces of a cone, or like ribbons. Are those gonna be like up and down like this, or are they gonna be horizontal like this? Those ribbons, up and down or horizontal? Up and down, right? So up and down. So we can imagine one of those like this. And the key that we saw last time, it was that we don't want to use just our plain old cylinders. We need these frustrums so that the edges are based on what? ds, not dx. dx is like horizontal. ds is based on what? The rate of change of the curve, like the slope of the curve there. And that's what we want to model surface area. We saw it doesn't work. If you just do dx and just do the cylinders we had before, it doesn't work. It doesn't give you the right rate. So we need those ds's there. Okay, so we want to rotate the curve on the x-axis. We want to define the rate of change of surface area with y as the independent variable. Okay, can you do it? We just want just the rate of change now. The rate of change of surface area using y as the independent variable if we're accumulating these ribbons or frustums. Okay, so again, we're using y as the independent variable, and we're going to accumulate these ribbons. Go. See if you can write the rate of times. I'm sorry. 2 pi times g of y. Okay. This is what we got. Okay, so remember this is the circumference of our ribbon or frustum. Okay, and so it'd be 2 pi r. So what about that? G of y. Is G of y the circumference of this ribbon? Or I'm sorry, the radius. Is G of y the radius of this ribbon? Is that right? What is the radius? The radius is from our center of rotation out to the edge. Is that G of y?
No, just y.
It's just y. That's the y coordinate. What does g of y equal? X. G of y is x, right? So g of y would be like this dimension, or like this distance from here to here. The distance from the y-axis out to that ribbon. So we want 2 pi times just y. Do you see it? Because the radius of that ribbon is simply y. G of y is an x-coordinate. And then what about the rest? 1 plus g prime of y squared, or dg dy. How's that?
That's good, because that's ds.
Right, that's the ds. Okay, so is that what we said? Okay, so now, and I call that r, the rate of change of the surface area for the function g. So I call it rsg. And our independent variable is y. So now you're going to write the surface area function. And so the advantage of writing this rate function first makes your surface area function a lot easier. If you can get that rate function right, and you get it in terms of y, now writing the surface area function itself is a lot more simpler and concise. Go. So now we want the surface area function still with y as the independent variable. So that's going to be s g of y. So you're figuring out what is that. So this is going to be capital S is surface area of g of y. Is there a question? Yeah.
Yeah, so the rate function you have, if the rate of change on surface area, is that also the area of just crossing? Is that 2 pi y squared over
Let's see.
The area of the ribbon, right?
With a dy. To get that, so to get a d, you're talking about d capital S. A d capital S would be the area of the ribbon.
Yeah.
That would be the rate times dy.
Okay.
But without the dy, it's the rate.
And that,
So that's just the rate. But if you multiplied that rate by dy, then you'd have the area of one ribbon.
okay.
Yep. Yep. Okay. S sub g of y. What will that be? Javier, did you get that? Why do you have headphones in? What? So did you get that?
So it would be an integral from
Integral from
a to y,
a to y.
and then your rate function r of s of g of y, or t and times dt.
Okay, r and the rate function with respect to t dt is what he said. That's what I had to. Is that what you put? So the integral from a to y of our rate function evaluated at t dt. Any questions on that? Does it make sense? All right, and now I want to get the whole, I want to represent the entire area of the piece of the horn. So I want to represent that entire area. What will the entire area be? Kylan, what do you think?
It's
S of G
of
1, comma 4. So starting from 1, because it's in terms of y. So the first ribbon has a y value of 1, and the last ribbon has a y value of 4 out here. This big, the largest one. I got 51.18. 51.18. So that would be how we'd represent the entire bell of the horn that's been cut off there, or the surface area. Okay? Now I want to graph the surface area in the right-hand pane. I want the independent variable on the horizontal axis and the surface area on the vertical axis. So this one was the arc length. So let's get rid of that one. Now I want to graph surface area. And I want what? I want my independent variable on this horizontal axis, and I want surface area on the vertical axis. Go. Write it out. What will it be?
No, it's
Okay, so he wants y equals s of g of 1 comma x. And then we need the apostrophes to make it, so you got it. And so I want to graph that from 1 to 4. And this 1 and this 4, are these x values or y values? They're y values on this axis, right? They're y values on this axis. And so like the other one, as we start from 1, and then as y goes up to 4, we accumulate surface area. And there's a lot more surface area than there is arc length, right? So that's why I had to really zoom out here on the... So that arc length just was something like, the whole arc length was, how many, like 3 units or 3 or 4 units like that? Okay, but then surface area is going all the way around the x-axis, and it's this kind of two-dimensional surface, so there's a lot more of it. So when we get to 4, we're at 60. So let's interpret this point. 3 comma 28.3. Interpret it. Tell the person next to you, what does that mean? This point is 3 comma 28.3. Okay, right. So in the original graph, when y is 3, the surface area is 28.3. So let's draw that amount of surface area. So y is 3 is like this. So we're only talking about then, that was bad. A part of it, right? The part of it up till when y is 3. So it's like this part of it. When you get all the way from y equals 1 up to y equals 3, that black, the part that I shaded black, that much surface area is the 28.3, corresponding to y getting to 3. Okay, so now here, this is the important part. So now I want to redefine the curve g as a function of x named f. So if x is ln of y, if g of y is ln of y, then what would, I want to redefine the same curve as a function of x. What would it be? F of x equals what? Anyone know? ln of y. If I want to redefine the exact same curve as a function of x, then f of x would be what? It would be the inverse of this. What's the inverse of ln of y? If you thought e to the x, you were correct. So now it's the same curve, but now defined as y as a function of x. Now I want to use that. I want to still rotate around the x-axis. It's the same shape that we're looking at. And now I want to define the surface area as a function of x with the independent variable. Go. So it's the same exact shape that we had before. Same ribbons that go up this way. But now we want to define the... So now it's going to be 2 pi. The radius is still y. It's the same ribbons as before. So the radius is still y. But now as our independent variable is x, we're going to need 2 pi times. It's still 2 pi y, but in terms of x, that'd be 2 pi f of x, or e to the x, times the square root of 1 plus. Now it's going to be f of prime of x squared. So there's our rate function. Did you get it? So it's the same ribbon. It's the same y value for the radius. But now that y value is, if we need it in terms of x, it would be f of x. Okay, so then our surface area function would be this. Just take, so now your independent variable is x, and we're going to use that rate function we just wrote with t, dt. And I'm going to graph it over here. So, do you know what you're looking at here? So, looking at this graph, what is the independent variable? This is the new graph. These are x's. X goes from 0 to, actually, ln of 4. It's more than 1, ln of 4. So x goes from 0 to ln of 4. And this is tracking the surface area as x increases this way. And this one now, if you're looking at this graph, these values here are y values, the one we looked at before. And so this is tracking y going from 1 to 4 and tracking the surface area that way. But then when we get done, it's the same surface area when x gets to ln of 4 versus y getting to 4. It's the whole surface area of that whole thing.